July 3, 1938. Stoke Bank, England. The pressure gauge that would rewrite the laws of steam locomotion was climbing past every safety threshold that British railway engineers considered rational. Nigel Gresley's Alaniar Class A4 number 4468 Mallard, the streamlined locomotive that German engineers swore would destabilize catastrophically, had been accelerating for 12 uninterrupted minutes toward a speed no steam engine had ever survived. Traditional British locomotives from London's most established manufacturers maxed out at 90 miles per hour before wheel harmonics tore their frames apart. The Mallard just kept accelerating. Through the Yorkshire countryside's gentle descent, something impossible was taking shape. British streamlining technology was approaching velocities that European physics calculations declared mechanically suicidal. A teardrop shell covering 165 tons of steel and water where German engineers insisted only exposed machinery could dissipate the thermal chaos of high-speed steam power. Professor Heinrich Müller's technical papers called the design thermodynamically unsound. Sir Ralph Wedgwood's decades of railway experience told him the boiler would explode before reaching 110 miles per hour. Yet Mallard's driver watched the speedometer climb past 115 while the locomotive remained unervingly stable. Then the middle cylinder's big end bearing began disintegrating at 125 miles per hour. In the next 45 seconds, everything European engineering predicted about British ambition would either be proven correct or shattered beyond recognition. Morning fog rolled across Doncaster's railway works where Nigel Gresley stood examining blueprints for a locomotive that most British rail executives considered an expensive publicity stunt. The LNER board wanted faster London to Edinburgh service, but they questioned whether investing £8,000 in experimental streamlining made financial sense when conventional engines already provided reliable 75 miles per hour operation. Germany's flying hamburger diesel train had embarrassed British rail by demonstrating 100 miles per hour capability in 1933, forcing a national conversation about whether steam power had reached its evolutionary endpoint. The German success sparked fierce debate within British engineering circles about fundamental propulsion philosophy. Diesel advocates argued that internal combustion represented modernity while steam defenders insisted their technology still harbored untapped potential. Gresley belonged to the steam defenders, but his convictions were rooted in mathematics rather than sentiment. His calculations suggested that aerodynamic resistance, not boiler capacity or wheel strength, imposed the real ceiling on steam locomotive speeds. Traditional British engines featured exposed cylinders, prominent smokestacks, and rectangular cabs that created turbulent air resistance at high velocities. Wind tunnel tests showed this frontal turbulence increased exponentially beyond 80 miles per hour, requiring progressively more power to achieve marginal speed gains. What if the solution wasn't more powerful engines but less resistant shapes? Gresley's proposal involved wrapping an A4 Pacific locomotive in a continuous streamlined shell that would slice through air rather than batter against it. The design drew inspiration from aircraft fuselages and racing car bodies, both fields where aerodynamic efficiency had proven transformative. His preliminary calculations suggested properly streamlined casing could reduce air resistance by nearly 30% at high speeds, potentially enabling sustained 110 miles per hour operation using existing boiler technology. The board's skepticism ran deeper than mere cost concerns. They worried about maintenance accessibility, thermal management, and whether British metalworking capabilities could manufacture the complex curved panels that streamlining required. Professor Heinrich Müller arrived at Doncaster Works with the confident bearing of a man who understood thermodynamics better than the British railway engineers hosting him. The German locomotive expert had published extensively on high-speed steam limitations, and his consultation visit carried the weight of continental authority. When Gresley showed him the Mallard streamlined design mock-ups, Müller's response was diplomatically devastating. The fundamental problem is heat dissipation, Müller explained to assembled LNER engineers, his diagrams covering the conference room blackboard. Steam locomotives generate tremendous thermal energy that must escape to the atmosphere. Your streamlined shell will trap heat around the boiler, creating pressure instabilities that will compromise structural integrity before you reach 100 miles per hour. His analysis cited well-established German research showing that exposed locomotive machinery served critical cooling functions beyond simple mechanical access. The air rushing past cylinders, valve gear, and boiler casing carried away waste heat that would otherwise accumulate dangerously. Müller's calculations suggested that Gresley's enclosed design would increase internal temperatures by potentially 40%, stressing metal components beyond their fatigue limits. The warnings extended to wheel dynamics and track interaction at unprecedented speeds. Traditional British locomotives used three-cylinder drive systems with rigid coupling between driving wheels. This configuration worked reliably at conventional speeds but introduced harmonic vibrations that Muller's research showed became destructive above 95 miles per hour. The German Reichsbahn had abandoned similar high-speed steam experiments after catastrophic bearing failures that killed 2 test engineers in 1934. You are attempting to exceed the physical limitations that metallurgy and mechanical engineering impose on reciprocating steam power, Muller concluded. The diesel-electric future represents progress precisely because it eliminates these insurmountable constraints. I urge you to reconsider this expensive experiment before worker lives are endangered. Sir Ralph Wedgwood chaired the LNER board meeting where Muller's report received formal consideration. Wedgwood had overseen British railway operations for 23 years, navigating through post-war reconstruction and the Depression's financial pressures. His practical experience made him instinctively suspicious of engineering proposals that contradicted established operational wisdom. Gressley proposes we gamble £8,000 on a locomotive design that Germany's leading expert calls thermodynamically unsound, Wedgwood summarized for the board. Our shareholders expect prudent investment in proven technology, not experimental showpieces that may never achieve their performance claims. The streamlining adds manufacturing complexity without addressing the fundamental boiler and wheel limitations that prevent sustained high-speed operation. The board's financial analysis reinforced Wedgwood's concerns. Even if the Mallard achieved its theoretical 110 miles per hour capability, the speed advantage would save perhaps 12 minutes on the London-Edinburgh route while requiring specialized maintenance that would increase operational costs indefinitely. Conventional locomotives could be built for £6,000 and maintained using existing workshop infrastructure, making them financially superior despite lower top speeds. Gressley faced a professional crisis similar to Marion's wire rope dilemma. His streamlined locomotive design challenged established engineering consensus backed by credible European research and practical cost analysis. The difference was that steam technology's viability as modern transportation was itself under question, adding existential stakes to what might otherwise have been merely a technical dispute about optimal locomotive configuration. The blueprints that would transform British railway engineering covered every surface of Gressley's Doncaster office by autumn 1935. With limited board approval secured through relentless advocacy, he faced the challenge of converting aerodynamic theory into a functional steam locomotive. The Mallard would either vindicate his career-long belief in steam's continued viability or provide expensive proof that diesel advocates were correct about reciprocating power's obsolescence. Gressley's design innovations began with the streamlined shell that had provoked Muller's strongest criticism. Rather than simply wrapping existing locomotive components in decorative fairings, he integrated the aerodynamic casing as a structural element that actually strengthened the frame while reducing weight. The continuous curves eliminated the frontal turbulence that conventional locomotives generated, but careful vent placement addressed the thermal management concerns that German engineers had raised. The boiler represented Gressley's most significant departure from standard practice. Instead of simply enlarging an existing design, he specified a high-capacity system capable of sustaining steam production at maximum output for extended periods. The boiler pressure rated at 250 psi, substantially higher than the 180 psi standard for conventional British locomotives. This pressure increase required thicker metal walls and more robust welding throughout the pressure vessel, adding manufacturing complexity that tested Doncaster's metalworking capabilities. Perhaps most innovative was the double-chimney exhaust system that Gressley adapted from French locomotive experiments. Traditional single-stack designs created back pressure that limited how quickly steam could cycle through the cylinders, effectively capping maximum engine RPM regardless of other performance factors. The dual exhaust divided outgoing steam between two optimized flow paths, reducing back pressure by 18% and enabling higher piston speeds without mechanical interference. The wheel and suspension system required solving the harmonic vibration problems that had destroyed German high-speed experiments. Gressley specified precision-balanced driving wheels manufactured to tolerances measuring in thousandths of inches, with each wheel assembly dynamically tested at simulated high-speed rotation before installation. The three-cylinder drive configuration received careful phase timing that distributed power impulses evenly, preventing the resonant vibrations that caused catastrophic bearing failures. William Sparshott supervised the actual construction with methodical attention to every assembly detail. As Doncaster's chief mechanical engineer, Sparshott understood that any manufacturing defect could transform Gressley's theoretical innovations into practical disasters at high speed. His quality control protocols tested every major component beyond its rated specification, rejecting parts that met technical requirements but showed any irregularities that might propagate into failures under sustained stress. The streamlined shell's fabrication alone consumed 9 months of intensive metalwork. Each curved panel required custom forming using specialized tools that Doncaster craftsmen developed specifically for this project. The panels then underwent pressure testing to verify they could withstand the aerodynamic forces that 110 miles per hour operation would generate, with rejected sections melted down and remanufactured until they passed inspection. By March 1938, the completed Mallard underwent initial testing on conventional routes, gradually increasing operational speeds while monitoring every system parameter. The early results showed promising performance, but the real validation would require pushing the locomotive toward the theoretical limits that European engineers insisted represented insurmountable physical boundaries for steam technology. The morning of July 3, 1938 began with atmospheric conditions that experienced locomotive engineers recognized as ideal for high-speed testing. Cool temperatures reduced boiler stress while clear visibility would allow careful track monitoring throughout the run. Driver Joe Duddington had piloted express locomotives for 17 years, his hands understanding steam power's subtle responses with the instinctive precision that separated competent operators from masters of the craft. Gressley positioned himself in the dynamometer car directly behind the Mallard, surrounded by instruments that would record every aspect of the locomotive's performance during the upcoming speed attempt. His engineering team included representatives from British Rail's technical division, ensuring that whatever happened during the test would be documented with sufficient precision to satisfy skeptics or explain failures. The test route followed a carefully selected section of the East Coast Main Line between Grantham and Peterborough. This stretch featured Stoke Bank, a gentle downgrade that would allow gravity to assist acceleration without requiring maximum boiler output simply to overcome climbing resistance. The track had been inspected meticulously, with any questionable rail sections replaced and all switches verified as properly aligned. Mallard departed Grantham at precisely 4 p.m., the streamlined locomotive accelerating smoothly through speeds that conventional engines handled routinely. Duddington felt the familiar responses through his controls as steam pressure translated into forward momentum, the double-chimney exhaust creating a distinctive sound that differed subtly from traditional single-stack locomotives. At 75 miles per hour, the aerodynamic advantages of streamlining became perceptible. Where conventional locomotives struggled against increasing air resistance, the Mallard's teardrop shell sliced through atmospheric pressure with measurably less effort. Duddington could maintain speed with reduced throttle settings compared to his experience with traditional engines, suggesting Gressley's wind tunnel calculations had accurately predicted real-world performance. The acceleration continued past 90 miles per hour, entering velocities where British steam locomotives typically approached their operational limits. Duddington monitored wheel harmonics carefully, feeling for any vibrations that might indicate the resonant instabilities that German research had warned about. The precision-balanced drive wheels remained remarkably stable, their careful manufacturing showing its value as speed climbed toward unprecedented levels. At 100 miles per hour, the Mallard was traveling faster than any British steam locomotive had reliably sustained. Yet the stability remained solid, the streamlined shell doing exactly what Gressley had calculated, reducing air resistance that would have forced conventional engines to their maximum output just to maintain this velocity. Duddington eased the throttle forward slightly, watching the speedometer climb past 110 miles per hour as Stoke Bank's gentle grade added gravitational assistance to the locomotive's power. The speed record fell at 114 miles per hour, surpassing the previous mark set by Germany's experimental locomotives. But Duddington felt margin remaining in the Mallard's performance, the boiler maintaining steady pressure while the drive wheels continued their stable rotation. He made the decision that would create history, pushing the throttle to maximum and letting physics determine where the Mallard's true limits existed. The speedometer needle climbed past 120 miles per hour, entering velocities that engineering theory had declared impossible for steam technology. At 125 miles per hour, the Mallard was operating in a mechanical realm that no steam locomotive had ever survived. The streamlined shell converted Gressley's theoretical aerodynamics into practical reality, but inside the locomotive's machinery, forces were building that would test every component's engineering margins. The precision-balanced wheels spun at rotational speeds approaching 400 revolutions per minute, while boiler pressure maintained its steady 250 psi output despite consuming water and fuel at unprecedented rates. Duddington watched the speedometer reach 126 miles per hour, a velocity so extreme that the landscape blurred past his side windows. The track beneath the Mallard transmitted vibrations that any conventional locomotive would have amplified into destructive harmonics, but the careful wheel balancing and suspension geometry kept the ride surprisingly stable. 4:45 glorious seconds, Gressley's engineering vision was vindicated as British steam power achieved what European experts had declared thermodynamically impossible. Then the middle cylinder's big end bearing began failing. The component, stressed beyond its design limits by the extreme piston velocities that 126 miles per hour demanded, started overheating as its lubrication film broke down under the relentless mechanical forces. Duddington felt the change immediately through his controls, a subtle roughness that his 17 years of experience recognized as serious mechanical distress. The bearing failure didn't cause catastrophic destruction. Unlike chain systems that collapsed completely when any link broke, the Mallard's three-cylinder design distributed power across multiple drive paths. The damaged middle cylinder reduced overall power output, but the two outer cylinders continued operating normally, allowing Duddington to maintain controlled deceleration rather than facing emergency shutdown. Gressley's instruments recorded the entire sequence as the Mallard's speed dropped from its peak 126 miles per hour through a gradual descent back toward conventional velocities. The bearing damage would require repairs, but the locomotive had proven its fundamental design was sound. More importantly, the speed record was official, 126 miles per hour, documented by calibrated instruments and witnessed by British Rail's technical representatives. The post-run inspection revealed that only the middle cylinder bearing had suffered damage, while every other major component remained within acceptable operational tolerances. The boiler showed no signs of the thermal stress that Muller had predicted would compromise structural integrity. The streamlined shell had successfully managed heat dissipation through its carefully placed vents, maintaining safe temperatures despite enclosing the machinery. The precision-balanced wheels exhibited no unusual wear patterns despite operating at rotational speeds that would have destroyed conventionally manufactured components. The bearing failure actually strengthened Gressley's vindication rather than undermining it. He had pushed a steam locomotive to 126 miles per hour, far beyond what any engineer considered possible, and the only component failure was a bearing stressed beyond its design specifications by sustained operation at record velocities. This wasn't a fundamental flaw in steam technology but simply a parts failure at extreme operating conditions. News of the speed record spread through Britain's railway community within hours, carried by telegraph reports that struggled to convey the magnitude of what the Mallard had accomplished. A steam locomotive had exceeded 125 miles per hour, demolishing assumptions about reciprocating power's limitations and proving that British engineering could match or surpass German technical achievements.